Hello. It's Friday, and it's time again for Advent of Code. Um, my name is Kent Quirk. I am a software engineer. I've been doing software engineering for some 40 years now. And what I'm doing this month is solving Advent of Code problems live in Go for the education and amusement, hopefully, of people. So, let's figure out what we're going to do today. The challenge is going to be whatever day 18 is, and these are getting more interesting as they go on. They take a little longer to solve typically, and so this sometimes takes a while. Let's hope it's a little easier today, but let's see where we are. Day 18, operation order. Okay. Child would like us to help them with their math homework with different rules. Okay. The homework, our puzzle input, consists of a series of expressions that consist of addition, multiplication, and parentheses. Okay. Addition in parentheses indicate the expression inside must be evaluated before it can be used by the surrounding expression. Addition finds the sum of the numbers on both sides of the operator, and multiplication still finds the product. However, the rules of operator precedence have changed. So in school, many of us were taught, for me, it was my dear Aunt Sally, multiplication, division before addition and subtraction. For more modern students, I think PEMDAS, parentheses, exponentiation, multiplication, division, addition, multiplication, division, addition, subtraction, something like that. Like when I was in school, they didn't even talk about parentheses or exponentiation. So, whatever. But in this case, it's not the case. We're just doing left to right order, which is actually kind of the naive version of parsing. Like a lot of the early calculators didn't support the concept of nested operations. So if you did 1 plus 2 times 3, you didn't get 1 plus 2 times 3, which is 6 plus 1 is 7. You got 1 plus 2, which is 3, times 3, which is 9. So that is what this is going to be. They're asking us to implement a naive calculator. So the good news is, but it's a naive calculator with parentheses. So we do have to have the ability to continue an expression that's in partial evaluation. But as soon as we hit the right parenthesis, we're going to be able to collapse the calculation as far as we've got. So basically every right parenthesis is just an execute everything you have. Well, not everything, because nested parens would be interesting. But anyway, so we're going to have to write an expression parser. Let's just read the rest of it to make sure that we are explaining the steps. Here's what happens to this sample. Here's a few more examples. Before you can help with the homework, you need to understand it yourself. Evaluate the expression on each line of the homework. What is the sum of the resulting values? To begin with, get your puzzle input. All right, I am going to get my puzzle input. Whoa, that's a lot of values. Okay, this is a pretty comprehensive test suite, I guess, of our parser. So I'm going to put this into my 373 expressions. Yay. So that's our data. We have a bunch of examples. I am probably going to pursue this by writing a fairly robust test suite as part of this evaluation using Go's testing capabilities rather than feeding it input data and trying to evaluate those input data. So let's let's start thinking about the parser. So the question is, we're getting a set of lines. Each line is standalone, so each line is an expression, and then we have to parse through that expression. Now, Go comes with something called a scanner, and a Go scanner is intended to be used in the process of creating parsers and things like that. And the thing that I found about it is, in the process of trying to use it in the past, it's the specification. You have to write a thing that says, Go scanner kind of wraps this function that you provide that when you call scanner, you get one token at a time out of the scanner, and scanner manages all the state related to that. However, the function you write to that is a scanner, they give you some predefined ones in the language, but if you have to write your own, it's actually a fairly complex problem, because you have to deal with the fact that basically Go is going to give you a buffer, and they may or may not give you all of the buffer. And then when they get to the end of the buffer, then they set a flag that says, "Hey, we're done. There's no more after this," so that you can kind of handle it properly. But essentially, you have to have a case for what happens if I'm at the end, and you also have a case for what happens if I'm not at the end and I get to the end of a token, but I don't know if there might be more. And then you have to go back and you have to return a value that says, please give me more, and then it gives you more, and then you can so you're holding things in buffers, and it's a pain in the butt. And so I'm not inclined to use Go Scanner, honestly. It's just not. I have never found it to be a very useful construct for general purpose kind of parsing. Like, it's fine if you just need a list of words out of a file and you can use a predefined scan function. In this case, I don't think I'm going to use it. So instead, we're just going to write our own little line parser, and let's just go with that. So here's my data. Let's start with our main.go, and I am going to share my screen so you can see it. Yay, I remembered. All right, so this is our standard main.go that we always use. And we're reading our input file and we're splitting it up by lines, and then we're going, this was just our demo function. So we're going to need a func day 18a takes lines as array of string, and for line in lines, we're going to call evaluate result gets evaluate line, and we need the sum of all the resulting values. So total is 0, result is the evaluation of that, and total plus equals result, and return total, and oh boy, and this returns an int, and this is going to be day 18a. Alright, so that's our basic call, which is going to return the sum of all of the results of all of the evaluations. And we need to define func evaluate. Func evaluate s string, and it returns an int. And so here we are. We're going to iterate through the line as runes. So we're going to do for underscore c in s, range s. So for every range, we're going to switch on c. So we know we need to evaluate plus no, we don't have to do that. We do need left paren and right paren though. And we need space. We're just going to ignore space. So a switch statement, if you know you have a particular value and you're going to switch on all the individual values, then you can do the switch statement like I have here. The other way to do it is to just do a switch, and then each case is actually a conditional, and you can evaluate all the individual conditionals, and they're just evaluated top to bottom in order, and the first one it matches is the one it uses. In this case, I could either switch on all the values 0 through 9, and then each time through the loop, I'm accumulating a number I could try a little trick here. All right, so we have a couple things. One is, I can do the case statement where it's just a bunch of digits, or I can do kind of clean that up a little bit and do a conditional case. Now let's do the bunch of digits. I think that's a little better in this case. Case. Whoops. All right, and then the other question is, what do we do at the end? Because we're going to be parsing the string, and then we're going to get to the end of the string, and we could be in the middle. Like all of these first cases are fine. If we end on a right parenthesis, then we know what to do. If we end on a plus or a star, then we have an error situation. But if we end on a number, we basically have a calculation in progress. And so one trick we can use here is what's called a sentinel. We can take a sentinel and we can, we know we have a limited vocabulary here. We have a limited number of characters. So in this case, our parser can we can append a special character to the end that we don't think is going to occur in our grammar ever. And we can just use that and evaluate it along the way. So in this case, what I think I'm going to do is s gets an appended, well, what character should we append? Something that we aren't likely to use in an expression, even in a second evaluation. Well, you know what? At sign is not typically used in mathematics, so we're going to interesting. I guess I have to put it in quotes because I am appending to a string when you do this. You can append a rune to a string. All right. So now we've got the things that we're going to be processing. So first, we have a term that we are accumulating, which is a numeric term, and it's going to be 0. And every time we add a digit to it, we multiply the term, the current value of the term, times 10, and then add the digit. So let's deal with this case first. So if we have a digit, we are going to say term equals term times 10 plus, and the trick here is that if we subtract, since a rune is basically a number, we can take 0 minus character, character minus 0, and that gives us the, these characters are sequential in the character set, and so quote 9 quote minus quote 0 quote for single quotes is the value of that, expressed as a rune, which I have to convert to an int. So that now gives us our new version of the term. So, all right, we have a term. Now, when we see a multiplication or addition, we know we have been working on a term, okay? But we may have ended it already on a space. Well, I think I'm going to so we want to be able to have our expressions have either number star number or number space star space number, things like that. And the easiest way to deal with that is to just ignore spaces entirely. Rather than doing some things on spaces and then maybe conditionally doing some things on other values that aren't numbers, we can just process this. So we have a term. I think what we would like is actually to set a flag that says we're currently accumulating a term, because term by itself doesn't have information as to whether it's actually a real value or whether it's something fake. So instead we're going to have in term is false. InTerm true. So we set InTerm. If we are not in term, this is now an error. And obviously, all right, I'm hating this. I gotta do. We're gonna do this as an int. Evaluate is gonna return an error if it sees bad data. So instead of log.fatalf, we're going to return errors dot new. And here let's define a new error type. Type parse error struct. And go error type. Error is a thing that has an error function which returns a string, which is the error evaluated as a string. So a parse error is going to get the input of text is a string, position as an int, because this is just a one-line error, and error text is also a string, and then func, we have to implement error, parse error string. This will make it conform to the error interface so that I can throw it. Return format.sprintf. So we're going to emit a 3-line error. Here we go. This should be fun. Format.sprintf. %s, a new line. %s, another new line. And finally, the last new line, last s. This kind of goes against. I was going to format this error nicely, but let's not get that crazy. Let's just do I was going to put like a caret underneath. All right. And this is going to get e dot error text, e dot text dot position. Okay. And then, so that is now a valid error. And let's do a new parse error, which takes text string error text string position int and return ampersand parse error text position pause error text there, and I should reverse these two to be consistent. Oh no. Yeah, I will. For no other reason than the call of this should be consistent with declaration order. Let's do that. Okay. And actually, error text should be first. And I'm going to do this here as well. All right. So now instead, we're going to new parse error bad character s ix, and this is going to be and this is also true for this. It's not actually even, no, it's not. I'm going to comment this out for a minute because actually, all right, so say I have 3 times 5. I'm going to do 3, and I'm in a term. Then I do star, and now at this point I have to end my term, and I have to remember it, and I have to remember that I'm doing multiplication. Because then when I get my next term and I end that, then I'm going to evaluate the stuff that's come before. So what I'm going to rename this symbol to in number rather than in term, because term is going to have a special yeah, so if we, so one way to do this is if we make a stack of everything that's in process, then when we get, there are times when we can clean up the stack. So we take a 3 and we get the 3, and then we get the star and we go, okay, well, we can take that 3 and we can put the 3 in the stack, and the star can immediately go in the stack because we know we can't do anything with it yet. So we have 3 and star on the stack, and then the next thing we get is 5, and then we hit plus, and now we can say, oh, well, we can go clean up the stack of 3.5, 3 and 5. It's not a stack though, we're evaluating it left to right. So in a regular evaluation, we would it's a queue. Then we just start iterating through the queue until we either run out of the queue. Oh, yeah. So this is interesting, actually. This is, okay, so so if we push so maybe we should have done this as a scanner, or we can write our own scanner here, a tokenizer. We split this thing up into tokens, and each token is a string, and if the string is a number, then we evaluate the number. Yeah, that would probably be a cleaner, neater way to deal with this. So let's take our, I'm still gonna do what I did here with, we're gonna push it. No, we don't, if we have a tokenizer, we don't need to do this magic. So let's try this again. Func tokenize s string, and it is going to return an array, a bucket of strings, and possibly an error. So the errors are still a good idea. And we're still going to do this, but our case statements are a little simpler. If case either plus or, times or plus, left paren, right paren, tokens is a make string of 0 length, tokens append tokens Can I do that? Can I turn a rune into a string that way? I think I can. This case. Oops, sorry about that. This case, we can I think because this is we're just returning a group of characters in the same string. So digits gets to be a blank string, and then we're gonna do digits plus equals string C in digits equals false, in digits is true, and then if in digits, then tokens append token digits becomes empty again. In digits now becomes false again. And case space gets that, and I guess actually I am going to do this trick, because otherwise I have to repeat that again. Oops, I keep hitting the wrong key there. Actually, I don't need, I can just add a space, which is a valid sentence. It should never be a problem to put a space on the end of the string. And so we're going to do that. It's never going to disrupt anything we're doing. And now, so now, now that we're done with this, return tokens. And we need our default case, which is going to return new parser bad character in S at position IX. and we'll return whatever we have for tokens at that point, even if it's bad. You know, if you get an error back for, oh, of course I've got that completely backwards. There. And this is not false, it's nil. Oh, new parse error needs another curly brace. Oh, and I don't ever want to return a parse error by as a pointer. I want to return the object itself. Okay. So now that we've done this, we just delete evaluate for a minute. Well, no, we're going to make it useless. We're going to delete all this stuff. Yay, okay, so I have a structure back again that I can live with, but I'm going to build some tests for tokenizer. So let's go generate unit test for function. Nice little feature of the Go plugin for Visual Studio Code generates a table-driven set of test cases for a function, and we're going to use that here to give ourselves a little bit of testing of our tokenizer. So the name can get interesting if you're going to do something complicated, but for the most part, the one thing I don't like about this is that if you just have one argument, it really would be just easier to just go this, take this, put it here. get rid of args entirely, and then wherever you have .args, which is just here, you can just do that, okay? And so now it becomes a little bit easier to write this. So A, and then my input string is, let's do the one we were talking about, 3 times 5. And want is an array of string 3 times 5, and we do not want an error. So that is our first simple test case, and let's run this and see if we get what we wanted. It seems fine. So now let's do 34 times 5. 34. That'll be test case B. And then we're going to test 589. We test case C. And then we are going to try some test cases that fail, like times. And in this case, I'm not sure, okay, okay, so this will return if there's an error. So we can just do, for cases where we want an error, we just do this. All right, let's run these. Just first test to make sure that, one of our test cases failed. So, oh, can you read this? You probably can't even see this because my picture is in the way. Here we go, hold on. So, we failed test tokenized D. Tokenized error was nil. And because of course it was 34 times, that is not a, there's an error that's tested by a tokenizer. Our tokenizer doesn't know or care that you can have times, whether or not you can have times. All it's doing is checking to make sure we have numbers or these special characters. So the only errors we can actually generate here are for bogus characters, like if I send a letter X. That worked. And then I guess the other thing that we probably want to test is that we get appropriate tokenization if we have spaces in here with separate tokens. So this should not return anything for the space, but I should get 2 numbers out of this, not 1. And see, okay, so that worked. So our tokenizer is returning a list of tokens, which is that line broken up into pluses and things. Let's make sure that all the tokens get evaluated properly. 1, 2, 3, 4, 5, 6, 7, 8, 9, 0. Plus star plus Actually, I can do this in one token, and then space plus star left, right, and what I should get out of this is 1, 2, 3, 4, 5, 6, 7, 8, 9, 0. Plus run that test. Great. Okay, now I feel pretty good about the tokenizer. It is doing what we wanted it to do. And returning all the tokens we wanted to return and none of the ones that we don't want to return, and so we're good. We have a functional tokenizer and we have tested and proven that it is. That, by the way, is a really useful technique. Even if you don't write tests for your whole end-to-end functionality, taking your critical support pieces and making sure that they have a robust set of tests is really valuable. So, now, we have a tokenizer that we like. Now to evaluate, we just say tokens error is tokenize S. Cool, that's a great start. If error, return 0 error. Okay. Now we have our list of tokens and we can start evaluating it. For T underscore T. So token in our list of tokens and we're going to need our accumulated result, which is going to start at 0, and then we're going to switch on, we're just going to switch, and then we're going to do tests. If I want the fastest way to evaluate the first character of, I want to know if it's a digit. Now one way you often do this in, like if you're writing real parsers, is that the tokens, instead of being just a bucket of strings, the parser can go, oh, I actually know what the value of this thing is. Let's just throw the value in, and we create a special type for the token. And that is not a terrible idea. Let's just see how tricky this gets. If it gets it all tricky, I'm just gonna, yeah, case. So what is my strings dot contains any. So case strings dot contains if that contains the string corresponding to T, let's call it the 0th character of T. Actually, I'm going to do the slice of T that is the 0th character rather than converting the 0 character to a string. That's actually probably, do string T. Oh, but that's a byte, not a rune. No, I do think this slice is safer. So t from t up to 1. So if the 0th character of that string is in the set of numbers, then we're going to see, let's make a collection of things we got to parse. We got to process. Then terms I can't have an error here from strconf.a t because I know that my tokenizer will only will only have a digit in there if it's all digits. So this is safe. So I take that term and I terms dot append terms term. We'll just hang out a minute. We may come back to that case. T is star action is current. We're gonna make action. Come back to this. If we get a star, we're going to say action is a star. Action is T. And the same will be true for, okay, so in this case, either star or plus, our action is that. T is left paren oh, really? So 3 times 5. So when we get to the second term, and we've just figured out that we have 2 terms, we can look and see if we have an action. Or whenever we apply a term, we can say, do we have an action? If we have an action, we can apply it. Otherwise, we can just append. So let's see what happens. If we go if action is not an empty string, I may not like how this is nesting, but let's find out. space star. In the star action, we can immediately multiply we want to multiply our two terms. We assume if len of terms, is less than 2, we have an error. Return nil, return 0, comma, new parse error. Inappropriate star. This is unfortunate because I don't know where that token came from anymore. So again, have we made a token structure? We could have put the numbers in there. You know what? I'm gonna do that because it feels like a useful exercise. So we are going to create a token structure. Func token token. It's not a func. Type token struct, and it's going to have the text, which is a string, the position, which is an int, a value, which is an int, and the value may not be filled in if the token isn't a value type token. And that's okay. I don't mind that. This is the kind of thing where you can like create this base type and then have values for some of them and all that kind of stuff. I'm not going to do any of that, but I am going to use this and then store in a structure of these things. So, sorry about the dog barking. There's nothing I can do. The mailman's here. The dog's gonna bark. Ain't no way to stop him. We've tried. You basically have to hold him the entire time and keep him away from the windows. And he's now going to bustle through the room, breathing heavily, because that's what he does. All right, so instead of returning, we need to return this bucket of tokens. And instead of so here we're going to, so this is now token, and we are going to parse its value once we have it. text is oh, whoops. Oh no, this is correct. Text gets digits. Position gets IX. Now, this is actually wrong. It's at the end of the position, but I'm not going to worry about keeping track of the beginning of the position. It's not worth it. This is just for error messages. And we could fix it later if we ever needed to. And the value in this case is going to be 0. So I can just, oh no, value here is going to be val, because this is the place where we do all right. I don't like that, but I'm going to do it anyway. And then instead of string C, we get token, curly brace, enter, text becomes string C, position becomes IX, which is correct in this case. And we don't care about value because it's just going to be 0. So we can do that. Save it. All right, so this is going to return tokens, which is good. But now our tests are wrong. So where else do I have errors here? I'm not using oh, yeah. So So another useful thing is to make your switching statements. We can make our switch a lot simpler later by switching on token type and including token type when we in our tokenized function. So we're going to do type token type and type So here we have to say, now we have to say token type number. And then here yeah, all right, I am going to do a little sleazy thing here. At the beginning of tokenize, I'm going to have ttypes equals map of rune to token type, and it is going to be star mult plus add left paren l paren r paren, and that's that. And there. Oh, it's not token type. It's just type. There. All right. Now I can go back to my main, and these tests won't even compile now because so now this becomes one of token, and actually all of these things that say array string now become token. Yeah. I'm just trying to avoid having to get like crazy ugly token definitions here. Now I don't have to specify token, and so I can do number three what are my other fields? Token type. Tokens have position 0. No, it's going to be 1. And its position is going to be, or its value is going to be 3. That's going to be, its value is going to be 3, and the other one is going to be mult star 0 1. Just going to comment these out for a second. Try saving this and see if the test runs. Oh, I got a bunch of errors. Line 117 cannot. Oh, I gotta fix this before I can. Wait, if I. No, because I need to evaluate. If I comment out all of these lines. That didn't mean anything anyway, so that looks more like I could probably test it now. Run the test, and I failed. Zero three one three 1 star 0 1 star 0 1. Oh no, it won't. That wants to be 1 0. 0535. Let's run it again. And that's correct. Okay. Wait. Oh yes, because it's the value is the last, not the position. Yep, okay. So now I can do B and do 34, and this is now 34, and this is going to become 2. That's going to be 34, and this is going to be position 2. It's still value 0, and 5 is still value 5, except that now it's at position 4. Save that, run that. Also okay. Now I can get and C oops 6 589. Run that test, and that's okay. D. Oops. D is just X. So that should still actually work. And E should just be the same as C without the star in the middle, except that the position of 589 is now 2 characters have gone. No, 1 character. No, 2. Oh wait. No, that's actually correct. Because E is 34 space 589. And F gets and now I have and its position is now 10, and then I have add mult L paren R paren plus times left paren right paren, and its position is no. So this is 1, 2, 3, 4, and the positions are 11, 12, 13, and 14. And it's F. And now let's run it. Probably forgot something. Okay. Zero 34, 234. Uh-oh, what did I do? Test E. Oh, I didn't want that mult in there. Duh. And test F failed. And did I just get the positions wrong? Oh. So comma 0. Let's try again. And it's okay. Okay, now it worked. So I changed my structure, I fixed my tests. Now let's go through and figure out how to fix this code, and we should be able to get on to getting an answer here. So, I may not even need this result right now. So terms, I'm making it a list of terms, and I'm going to switch t.type and case number Okay. Case L paren R paren. I wish my dog would shut up. Okay. And we need an index here. Oh no, we don't need an index anymore. This is good, but this now... Oh. T dot text. Oh, actually no, we still want this to be S, but now we want T dot position. But now that we're switching on type, we have a number, and we can throw it in as a term. So we're evaluating left to right. And we only have one action here. So it's useful to have a null token. And you want the 0 type for the token to be that null. So now I'm going to change all of these. And so we're going to var action is a token. So the empty token is now a null token. So then I can say switch on action type, and mult action equals T. So that's still good. Case mult but if we do have two terms, at least two terms, then we can take the first two terms, multiply them, and put them back on the list at the beginning. So terms is equal to instead of appending terms, in this case, we're going to do terms So what this is doing is it's saying make a new value for terms, and it is appending an empty array slice of ints with the value we get by multiplying the two terms plus the remainder of whatever was on the terms list. So we're basically taking the first two elements, collapsing them into one, and putting the whole list back together. So for the case of add, it's going to be exactly the same but with a different operation. Now if we were doing a lot of operations, I might be inclined to make this like a function here, and it, you pass it the terms, but so these are, we have two binary operators. If we had more, then making these into a looked up binary operator function that does this would be maybe a useful way to go. So inappropriate add oh and I don't think we're going to need a result at all. We're basically collapsing everything down to the first entry in terms, and so what I'm really going to return here is terms so now what happens when we do a left paren and right paren? What do you say? Should we see if this works first? Let's generate unit tests for this function. So evaluate now has, I'm going to do the same trick we did before. We're going to take this string and we're going to put it in place of args, and we are going to create test case 3 times 5, and what we want is 15 and we want no error. And we can get rid of the .args part. Fail. Cannot use type string in 8i. That's true. Main.go, line 118. T. Oh, and I don't need to do this anymore. So terms T dot value. And it passed. So our basic structure of 3 times 5 worked. Let's just make sure that, and I'm pretty sure because our tokenizer works, that we're happy about this. So let's go 12 times 25. We should have 300. And that's also okay. So that works. Now what happens if we have more than a couple? So let's make sure addition works. Plus 25, and that is now 37, and D is 12 times 25 times space 7 space, and that's 2100, and that is also okay. So this is doing the thing we wanted to do, and Now let's see what happens if we do 12 times. Oh, interesting. Oh, yeah. I would have thought that since at that point terms right, I'm gonna do this, and then when I run this test I'll get a number of things will print out. So 3, 5, 12, 25, 12, 25, 307. That's correct, 12, 25. 300. Oh, wait. Nope, that's not the right thing. Yeah, so what's going to happen here is when we execute an action, we're going to set the action type to null. And here we're going to say if action dot type not equal to null, return 0, new parse error. Alright, so now we have an error. Now we're dealing with that error condition as well. And that is correct. And okay, good. I'm not going to do any more testing right now. We're just going to start getting some real answers here. We have to figure out how to deal with parentheses. Okay, so for parentheses, the deal is when we get to a left paren, we want to essentially put we want to call ourselves recursively starting from here. With the remainder of the string. And then get the value back from that on right paren. Right, and sorry. So when we do left paren, we call we're going to say v equals a term here, evaluate s starting at, now our index is currently pointing at ourselves, so index plus 1 to the end of the string. And evaluate returns an integer and an error. Term can say terms equal terms, pen terms term. Oh, so here's a problem. We are returning, right now we're saying go from S to the end of S. And when we return though, where I was planning to return when we hit the right parent. And the problem with that is when we do that, we need to continue from where that right paren was and use the value inside that. So evaluate needs to possibly return a skip to value along with the error. Oops. No, this is worse than I thought it was. Hold on. I am this is not probably the right way to do this because I just forgot I'm not dealing with a string here, I'm dealing with a list of tokens. And that's not gonna fly. At least not yet. So if I move the parsing of the tokenization out of evaluate, and then I pass evaluate a collection of tokens, evaluate could also return a collection of tokens. Which would be the remaining set that was unparsed. Let's do it that way. So evaluate, instead of taking a string, we're going to take this code that tokenizes and we are going to put it here. Actually, I don't care. In this case, I'm just going to throw that away. So tokens token and now term okay. So now we're going to evaluate the remaining set of tokens. We're going to get a value back. We're going to, assuming there was no error, we're going to put the term we just got. We just calculated the term, so we have to thing we just got, so we got a left paren, and now we're going to, that means here's a new term. We're going to put that term onto our little list. So that's good. And then we are going to replace tokens equals remaining. I am not at all sure so we know, okay. Tokens equals append of tokens up to ix. So okay, instead of doing instead of doing remaining, because what I'm doing is I'm walking a list, and then I'm jumping ahead, evaluating part of the list, and then I want to throw away the part that I just evaluated. So this is not the right way to go in terms of returning the remaining tokens. Instead, what we should probably do is return the number of tokens consumed as an integer. And then these values for return we should return index, the number of tokens we have consumed. And then instead of trimming tokens, what we're going to do is we're going to say index adds consumed, and index, instead of saying index t range tokens, let's just do t tokens index. I feel better about that. I don't know if that would have worked just fine anyway. So when we get to a right paren, we should have properly evaluated our stack should be empty. No, it won't necessarily be empty because we may have just consumed Is there any circumstance under which right paren is valid? So actually r paren can't occur out here unless it's an error. So if r paren occurs at this level, return 0 ix new parse error bad paren t.text t.position. And here though we can say case r paren, whoops, if we get an r paren here, we have executed no, our action type is not r paren. Oh, right, we don't, yeah, no, I just had a number, and now I get to, and so I did my math, and now I get to an r paren, so no, this is the wrong thing to do. Now I just return terms 0 index nil. All right. That feels better. Oh, now this has to return that. Oh, so first of all, does it still pass all its tests? Oh, nope, because now evaluate once. So what I'm going to do here is I'm going to, since I trust the tokenizer, I'm not going to evaluate all by itself. I'm going to evaluate after I parse through test evaluate. So here, instead of, we're going to tokes error tokenize tt.s if they're not equal to nil, and one is an int, want2 is an int, and then all of these so 3 3 3 5, and I don't know what that's going to be. We'll see. Let's run it again. No. Echo 143. Got to want 0 for So that's fine. All right. So that much worked. Now I can add a little more. Let's start adding some parenthesis tests. What happens? Oh, the result of that should be 7. The number of terms should be high. 2, 3, 4, 5, 6, 7. Should also be 7. What do we get? Evaluate 1, 0, 1, 7. Evaluate 2, 2, 1, 7. Well, that didn't work. Why didn't it work? So, first, I'm going to comment out these tests just to reduce noise. And then I am going to print and see what the test looks like now. So tokens oh, these are my tokens. Okay, so first, oh, Shiner. Oh, Christmas time. We get a package delivery every 30 seconds. It's insane. Okay. We got 1, 3, which is the paren, 4, which is the, no, 3 is plus, 4 is paren, 2 is the number, times 3, right paren, okay. And then we call in on and we say 2 times 3, right paren, and something printed 2, 3. What printed 2, 3? Oh, multiplied 2, 3. So our paren what that should print is 6. But it did not. Oh, that was silly of me. Length of terms is not equal to 1. So we had a bad error. We had an error there. For some reason, the error didn't get propagated, though. Or I didn't properly evaluate it when it went up to the parent. Okay, so this came out to 723, which really shouldn't. Oh, wait. No. I should have skipped. Okay. Alperen where's my... Okay, I'm deleting this. And this appears to be correct. Okay. Gave me 0 and I wanted 7, and it gave me 6 and I wanted 7. So this is still a problem here. Now, Alperen is doing an evaluate. Run that test again. 630. So it says I consumed 3 tokens. I should have term consumed error, and then okay, nope, let's just see this. So terms is 1, now I have 1, 6, and consumed is now 5. I wonder if range is pre-calculated. So let's just do something here. Ix is 0, x less than length of tokens, ix plus plus. And now, let's see if that has any different result. Does not have a different result. Then I'm going to put it back to the way it was. Oh, maybe I needed ix plus 1 on right paren? Still on. I want to skip that current token. Oh boy. Okay. I'm sorry this is going so long, but hey, so it goes. Our left paren is tokens. So we push, and we pass in the remainder of the tokens, which we saw that we got right. And then when we pop, the result of this, we want to skip all the way to that point of the right paren. Oh, but we didn't evaluate. We have a trailing space. No, there are no more tokens in the chain at that point. Oh. So we return from this right paren, we get to here, and there's nothing left to do, and so we just return. We have to collapse the rest of the stack when we get the end paren. Because that has just added a term to the list. So we have to treat that like the same as number. So R paren, no, so after we get back from L paren, it's as if we just pushed a number onto the stack. So what we'd like to do actually is we could cheat and replace the thing that we just got with the evaluation of what was between the terms. So instead of just saying we'd have to modify tokens, which I don't like doing. Oh god, dog, shut the hell up. Okay, one way to deal with this would be to one way to deal with this would be to inject a new token into our list of tokens. Which is kind of ugly. Another is to pull this action type calculation out. Because there's still a pending action. Yeah, and then we just do action, and I can put that in here as well. So do action is going to take as a parameter the action now I am gonna, you know what I'm gonna do? I'm gonna make an action be, since the only two actions are multiply and add, so action okay, so here we're going to create a couple of actually we can make them local to this. Adder is stop function of int a or ab int returns int and return a plus b. Multiplier function of ab and returns a, return a times b. I can't believe I did plus equals. Colon equals. Type functor func int nil do nothing is func and in this we're going to say if action is not equal to do nothing, action equals multiplier shoot. Cannot compare. Alright. I'm sorry. I have been on this stream for almost 2.5 hours and I have other things I need to do. And so I'm gonna stop here. This is the way I want to go. I'm almost done. And then we'll have to see what part 2 is. And I'm sorry I didn't get there tonight. So it goes. Hope it's been at least semi-interesting or useful to you. Learn something maybe about parsers and things like that. Not so much about solving this puzzle, but hey, that's okay. So thank you for watching. Hope you have a great day, and see you around.